Yes, sir. Just give me 1 second.
Just want to tell you guys. So this
Yes.
video, recorded video, na, it will be posted. So just okay, go ahead. Yeah, let's see. You have your main
Yes, sir.
on line number 24. So you say print f, enter the number of elements. On line 27 and 28, you read the number of elements. And on so one point I would like to mention here, if you see on line number 29, you are declaring int a of 10. It is okay, but yeah. So at some point I told you know that there is C89 standard and C99 standard. This particular way of declaring an array where the length of the array gets created depends upon a value n which is read at runtime. It is possible in C99 but not in C89. Anyway, it's good. So and then line 30 to 33, you read input, you call the sort function on line 34, and then you print it from line 35 to 38. So great. So we keep be there. Yeah, main. I hope all of you are with me. It's very nicely written code. The main function you can all see. It is very well indented. It is, the spacing, everything is so beautiful. And you're calling the sort function with, it has two parameters. One is the base address of the array. Other is n, that is the size of the array. Okay, let's go to the sort. Okay. So now the sort function, the first parameter is a one-dimensional array. So the particular way in which it is declared, int a, followed by square brackets, that is how we declare, we say that we are passing an array as a parameter. And of course, the second parameter is simple. It's a scalar variable. It's a scalar value. That is the number of elements. So on line number 10, if the number of elements is equal to 0, you don't need to do anything. You simply written awesome. Otherwise, what do? You take min is equal to a of 0 for j is equal to 0. You have a loop in which you find the smallest element. You maintain the index of the smallest element, right, Shreyansh?
Yes, sir.
Okay. So Shreyansh is maintaining the position of the smallest element. Excellent. That is j always contain, the variable j always contain the position of the smallest element. Initially, the position of the smallest element is 0, that is there on line number 12. So he wrote a very beautiful loop, and yeah. And then once we are out of the loop, so you swap a of 0 with a of j, where a of j is the min element.
Yes, sir.
And now you sort starting from a of 1, n minus, the number of elements got reduced by n minus 1. Fantastic code, Shreyans. It's beautifully written. So,
Yes, sir.
yeah, I wouldn't have done better than this. It's really well written code. I hope, no, the I want to see line number 22, the whole thing very beautifully. The whole approach is very simple. You have an array and you find the smallest element, you put it in the 0th place. You swap a of 0 and a of j, where a of j is the min element. And then after that, no, you saw the rest of the array. The rest of the array starts from a of 1, a of 2, a of 3, so on up to a of n minus 1. But the size of the array now is reduced by 1, n minus 1. Good. Very good. And so on line number 10, if you see, so you keep on recursing, and on line number 10, the recursion ends. When n is equal to 0, there is nothing that needs to be done. You return.
So I just have one question. So
Yeah.
can't we make this as a void function? Is there any way? Because we will have to return, or else it will be like an infinite loop, right?
Yeah, we can just make void. It doesn't matter.
So, but if we
Yeah,
make it
because
void,
it's
then
not
we.
going to change anything. If n is equal to 0, you just say return and you make it into a void. It's not going to change anything.
So, but in void we can't return, right?
No, no, there is nothing to return. Na? On line number 10, you just say return, don't put return 0. You make line
Okay.
8, you just make void. You go to line 10. Yeah, just return. That's it.
Thank you, sir.
You're not returning anything now. That's it. You're good.
So should I stop sharing?
Yeah, let's see if there are any questions. Uh, I'm seeing the chat. Are you all with Shreyansh? It's a very beautifully written code. The way the code is indented, the way the variables are declared, the whole structure of the program is very neat, and the logic is also written excellent. Is there anyone? Uh, does anyone want to share your code and show? This is I'm very happy to see that piece of code. If anyone feel like you can see one more code and. So let's see, let's say there are two people volunteered, Vaibhav and Balaram Krishna. We will see both of your codes. Okay, just two because we don't have much time. We have to move on. So Vaibhav and Balaram Krishna, we will see. All right. Narayana, you will get an opportunity at a different time. So Vaibhav, you can go ahead and share your screen.
Yes,
See, if you think in the right way, how easy to write the whole
so
code.
is my screen visible?
Yeah, your screen is visible. So you wrote a 2D. So Vaibhav, the first thing you should do is you right click.
Okay. Right click.
Yeah, do format document.
Okay. So,
Yeah. So your code should be indented. Okay, then it makes very easy for you to understand, uh, for anyone to understand what you're trying to do. So did you see how the code is before and how the code is now? So
yes,
if you just format the document, then how that, like for example, the for loop from 15 to 23 is contained in the outer for loop from line number 13 to 24. It's very, very clearly visible. Before that, it's not clear, for example. Okay, good. Anyway, so now let's get started. So line number 6 to 10, you are reading the input. Okay, so you made the length of the array to be 10. So the maximum number is 10. So one more thing you're also doing is the user always have to enter 10 numbers. That's okay. That's fine. So, and then on line 11, you have small is equal to a of 0 and good. So I see what you are trying to do. Uh, in the inner loop, so in the outer loop, when I is equal to 0, you try to find the smallest element. And when I is equal to 1, you try to find the element from which is at the position 1 in the sorted array, so on and so forth. Uh, Very cool code. And this is a very good contrast between the code written by Vaibhav and Shreyansh. This is an iterative piece of code, and whereas what Shreyansh has written, it's a recursive version of the code. Both are good, but I hope you are all able to see the logic here. Is there anyone
okay.
who has questions in this code? Is everyone doing all right? So, does anyone have questions? So when in the outer loop, When I is equal to 0, the array that you consider is a of 0 to a of n minus 1. In this case, a of 0 to a of 9. When I is
Yes.
equal to 1, the array that you consider is a of 1 to a of 9. When I is equal to 2, the array that you consider is a of 2 to, yeah, a of, a of 2 to a of 9, so on and so forth. And every time you kind of, from the section of the array that you are considering, you try to find the smallest element.
Yes, sir.
Good.
So we can
Awesome.
actually
Yeah.
we can remove the 10. Like we can put the integer n and take the
Yeah, yeah, it's okay. You can do it later, but the logic, yeah. So you can, but the important thing I want everyone to understand here is there are two different ways in which this code is being written. One is recursive version written by Shreyans. The other is iterative version written by Vaibhav. And I want you to understand these two different versions of the code. Good. So Balaram Krishna, you can unshare. We will see Balaram Krishna's code and then we will
yes, sir.
move on. Okay, Balaram Krishna, go to the main. So length of the array to sort. You create an input. Okay. So you have a read array function in which you read. You have the sort function and you have the print array function. Good. So you read array, you sort, you print the array. Now let's go to the sort and see what happens. Huh. Smallest of, okay, you are trying to find the smallest. You are finding the pointer. Your smallest returns the address of the smallest element in the array. You are swapping it with a of 0. And okay, and you recursively call the sort if the length, if there is at least the length of the array is at least 2, right? That's what you do, right? If length of the array is at least 2, then you will recursively call. If it is 1, you don't need to call it. So in this whole thing, so I think some of you could be, the important thing here is on line 53, uh, Balram is calling the smallest function, and he is trying to find the smallest element in the array A. But the interesting thing is he returns the address of the smallest element. Address of the, like for example, if ith element, that is if a of I is the smallest element, he returns the address of that element. And then he uses the swap function to swap the element at index 0 and the ith element. Go to the smallest function, Balram. Great. Yeah. So I see what you are trying to do. I hope others are also able to see. He is trying to keep a pointer. So what Shreyans did, he tried to maintain the smallest element by using its index, that is j. But whereas Balaram is using an address, he is always keeping track of the address. Both are equivalent approaches. Okay. But in this case, Balaram, we don't need to use pointers. It's better to take the approach taken by Shreyans, while this approach is also perfectly valid. But possibly this code is a little bit more complicated, and maybe this may have in terms of performance later on we will see your code might be slightly less performing than compared to Shreyan's code. But both are equivalent. So you are trying to keep track of the smallest element by maintaining its address, and Shreyans is trying to maintain the smallest element by maintaining the index of that element. So Balaram, I have a question for you. Can you rewrite your smallest code, this function, in such a way so that instead of returning the pointer, it returns the index j? It returns the index j rather than the pointer. You understood, Balaram, what I'm asking for? Maybe you can do it. So you can you copy this and just so that all the students can understand what's going on. Can you copy this whole code and paste it in a new file, and we will rewrite this code? Yeah. I'm very happy to see your codes, and it's I feel good, and excellent work, guys. I hope everyone. Is there anyone who has trouble understanding this code? This code, all the three codes that we have seen. Yeah, you go to. So Balaram, I can't hear you. If you want to talk, you can. Yeah, so you are changing this, right? Yeah, so just make yeah, that one. That's it, and then so go to line 19 first. Actually, you make int small is equal to 0, not a of 0. You or no, maybe you're comparing it with. Okay, just make small is equal to 0. Yeah, if length is equal to 1, you return small. Else if and then do one more thing. You don't need the else there, because you just remove the else part unnecessarily. Why do you want that else? And indent the code. It's all good. So can you indent? Go. Yeah, it's all good now. Yeah. So now it is. Now you have. If the length of the array is 0, is 1, then you return a. That's the index as 0. If length is, and you don't need if length greater than 1. Yeah, you don't even need that, right? I hope you don't need that unless you're calling length with a different. Yeah, it should be good. Remove line number, the square brackets, the flower bracket there. Format the code, right click. Maybe we keep that else part there. You're trying to find. You should have on line number 19. Go to line number 19. If length less than or equal to 0, if no start, just length less than or equal to 0, then copy the line number 35 to 38, cut line number 38, 35 to, yeah, paste there. Yeah, remove the else. After line number 24, you press an enter key, you give space, good. So if length is less than or equal to 0, yeah, so we give this message. If length is equal to 1, great. So now let's do this. If a of I is less than a of small on line number 31, because small keeps track of the smallest, is the index of the smallest element, then small is equal to I. That's it. And then now go to smallest, you get int p small. Yeah, and then what should we have here? A of p small. Awesome. That's it, guys. That's uh, yeah. So now this is a very very modular version. So you have you call from main, you call smart as the sort, and you find the smallest element, the index of the smallest element, you swap it with a of 0, and you recursively call the sort function. Fantastic. Um, Very nice code, Balaram. And I hope all of you are with me here. I am thoroughly enjoying. I'm not sure about you guys. Is it all good? Prachush, in either of the two codes, we are trying to fix the smallest element. And once you have the smallest element, now we repeat the same process in the rest of the elements. That's the plan. So if you keep the share, can you, yeah, who is this? I forgot the name. Balram, can you permit me to annotate the screen? Yeah, thank you. See, those of you just want to kind of say this is what is happening here in the code written by. So this is your array. I'm just writing this array in a horizontal way. This is index 0, index 1, index 2, index n minus 1. And let's say your minimum element is present somewhere here. So what we are trying to do is we are trying to find the index j or small. So Shreyansh used variable j to keep track of the smallest element, and Balram used no, the variable small. Balram, can you go up a bit to go to, yes, okay. So, and then what is happening here is, so initially we think, that A of 0 is the smallest element. So let's say this is our current estimate. Initially we think that this is the smallest element. And then as we keep seeing more and more elements, we keep, let's say this could be 4, and this is 10, this is 0. Initially, like for example, you start with the estimate that a of 0 is the smallest element, and when you see a of 1, your estimate doesn't change, and then when you see 2, your estimate changes, in which case, no. So initially j will be equal to 0. In the next iteration also j will be equal to 0. That is when it is examining a of 1. But then after examining a of 2, its estimate improves from j is equal to 0 to 1, because a of 2 is smaller than a of 4. So like that, we iterate through this whole array and find the smallest element and we'll figure out that this is the smallest element, and we swap it with this. We swap a of j with a of 0. Once we swap a of j with a of 0, then what happens is we just focus on the rest of the array. So we focus on so after we do the swap, so we focus on this from a of 1 to a of 0. And that is what exactly the code is written. Can you go to the sort function, Balram? Yeah. So in the sort function, in the array A, Step 1 is find the smallest element. Step 2 is swap the smallest element with the a of 0. This is step 2. This is the swap. What is step 3? You sort the rest recursively. And when we try to sort the rest recursively, the same process will be applied. And the most important thing here is from the sort function perspective, when we pass the base address of a of 1, it just doesn't care anything about whatever that is there before. It just thinks of this whole thing as a array starting with the index 0. So that is the cool part here. Okay, that's the cool part here. Right? So let me see if there are any questions in the chat box, and then we will yeah, fixing the largest, or no, if you want to do descending order, if you want to do ascending order, or no, you can use multiple approaches. uh, yeah, but the base idea is this. Are you all with me here? Any questions? Anyone has any problem? I hope all of you are with me. This is so those of you who are able to write this code on your own, I think you reached a major milestone in the programming course. And many times in practice, the logic, in practical problems that you encounter, the complexity will not be much more than this in terms of the logic. In terms of the problem size, it could be large because there are many components to the problem, but in terms of the logic per se, it will not be much bigger than this. So if you are able to write the selection sort code by yourself, either the iterative version or recursive version, then I would say, so you reached a very good milestone in this programming course. Okay, and you should that would be good accomplishment for this year. Right, so let's keep going. So maybe you can unshare Belram. Great, thanks a lot. So now sorting is an important problem. The next important problem that we would like to look at is searching. So given a list of elements, uh, we would like to search. So there is an array, and there is an array of elements. How can we search? And we want to know in this array whether there is a particular element with a particular value, whether there is an element with a particular value. Like for example, uh, like what do we do? So let's say you you go to academic office, and no, they want to you want to know how many marks you got, or you want to get your transcript. And if you ask them, hey, I would like to get my transcript, so they'll ask your roll number, and what do? They check your roll number against the database of roll numbers they have. So usually these are what are called as key value stores. There are what are called as key value stores, because what is the key? The key is the roll number. And what is the value? The value could be your transcript, or it can be many of the things. Okay, so roll number is the key, and the value could be anything. It depends on the context, right? So let's take a simple problem. We would like to check, given a list of numbers, we want to search whether a value that we have at hand is present in that list or not. So that is the problem at hand. So what approaches that we have to solve this problem? So what approaches?
Mm. Check first element.
Okay. So checking each index. Good. So you try one element at a time. Let's try to write code for this. Let's try to. Yeah, let me. So we have an algorithm, that is the algorithm which you are suggesting. It is what is called as a linear search algorithm. Okay, it's a linear search. So in the linear search algorithm, so this is uh, so this is what we do. So let's say we have an array A int. So we have the elements 10 minus 1, 4, 6, 8. So we are initializing this array at the time of declaration itself, right? And you want to check. So you have this thing. So you want to say, yeah, printf enter a value to search, enter a key to search. And let's say I have something like a variable called as key. And so let's, for the sake of, let's say, get search for key, and you pass A, and if the key is present, it returns the index position, key position, the place at which that key is present. That's what we are looking for. And yeah, so what do we do here in the search function? It is int search, int A, int key. Yeah, so it's nice that we need to, without knowing we cannot know the length of the array, so we will have int size of the array also. Let's, so in this particular case, the size of the array is 5. So yes, then. So what's the problem, Siddiq? I don't understand. So there is no problem now. I can. No, you can just put empty also, I think. In main, that is allowed, Siddiq. On line number 13, that is allowed. If I, so on line number 13, the compiler automatically infers that the size of the array A is 5 based on what is there on the right hand side of the equal to statement of the assignment statement. So if you don't find the key, you return -1 saying it is not present. If the key is present, it will be found in that if statement somewhere and the index will be returned. If it is not found, it will return -1. In my case, line number 13 will be allowed because, the even VS Code editor, it is not showing any problem. And what should we do here? If key pos is not equal to -1, then what do? Printf key found at index %d /n key pos, else printf key not found. Excellent. So let's compile this code and see what happens. So GCC linear search.c, syntax error, line number 3. What's the problem in line number 3? Oh, no. This is GCC, I should use. Let me use. So now what are the possible keys? Let's say if I enter 10, it says key found at index 0. If I enter -1, key found at position 1, because on line number 13, you can see -1 is present at the array index 1. Let's say if I enter 2, then it says key not found. Are you all with me on this code? It's extremely simple piece of code. This is the baseline. Does it make sense? So how many comparisons, if you see, when we think of algorithms, we kind of say what is called as a best case and worst case, etc. In the best case, how many comparisons will be required before a key is found in the best case? Yeah, 1, because you search for the first element and it so turns out it's a hit, and the best case is 1. What is the worst case? 5. Or if the length of the array is n, it is n. Worst is equal to 6. Awesome. So now the question is, is it possible for us to do better than n, where n is the size of the array? Is it possible for us to do anything better than n? That is the question. So here, do you think it is possible to do? Yeah, Shreyan says it's binary search. So here, if the array that we have, it's not a sorted array, but let's say if it's a sorted array. Okay, if it is a sorted array, so sorted means, like, for example, here you have -1, you have 4, this is 6, this is 8, this is 10. So now if this array is sorted, this is bad luck. So the array is sorted. If the array is sorted, then let's say if you are searching for element 10, if you are searching for element 10, what do? You go and search for look at the middle element. You compare 10 with element 6, and 10 is greater than 6. 10 is not equal to 6, and not only 10 is not equal to 6, 10 is greater than 6. So what do? You search for the element in this section. And then again, you kind of try to find the middle element here in this section and compare it. But let's say if you are searching for 2, then what happens is, since 6 is not equal to 2, but 6 is less than 2, if the element is present, it should be present only in this section. It cannot be present in this section. So you discard the right section and you try to search for it in the left section. So generally speaking, if this is your big array, so what you do is you go to the middle element, and then what you do is you check if the element is equal. If it is equal, then it is a hit. If it is, there are three cases. What is case one? Case one, let's say this position we call it as mid. Okay, and the key, if A of mid is equal to the key that you are looking for, this is case one. Case two is A of mid is less than key, and case three is A of mid is greater than key. So these are the three cases, and if A of mid is less than key, so let's say the key is equal to whatever the key is, then what happens is the key should be present on the right section. So if this is the case, let me use this color coding. If this is the case, yeah, let's assume that the elements are arranged in ascending order, because let's say if this is the case, this is case 2. So this green is the case 2. If this is the case, then you look at the green section of the code, because key is greater than A of mid. So if at all key is present, it should be present in the green section of the array. On the contrary, if this is the case, that is A of mid is greater than key, if this is the case, if this is case 3, then the key, if at all present, it should be present in the yellow section of the array. So you confine your search from here to here and from here to here. And anytime that you can specify the array section by using the base address of the element and the length of the array. Like for example, if you want to recursively search this, what you can do is you can say search base address of search base address of the array, and the size you can kind of say n over 2. And on the contrary, if you want to search in this green section, you can kind of call the function search no, address of a of n by 2 comma, and the size of the array is n by 2. So if you want to search in this section, this is how you make a recursive call. And if you want to search in the left side of the section, this is the recursive call that we should. If the number of, so these are the cases I would like. The problem I have for you, is this. I kind of broadly outlined the logic. So I want you to figure out the details and write the code for me on, this is Tuesday, right? On Thursday class, can you try to give a shot at writing the code for this, for the binary search? This is what is called as a binary search problem. Can you give a shot at this one, at this problem, the binary search problem, and get back to me on Thursday? I would like to, the way we have looked at the code now, I would like to show your code to the class and discuss the code. I noticed it from today's uh, experience that you are way better than me in writing code. So I want to see your code and explain it to the rest of your classmates. Okay. So here is, if you see, I leave the code, writing code for you for this binary search problem to you, and you can show it to me in the next class. But in the rest of the 5 minutes, I would like to make few observations on this problem. Let's see. So here, if you see in the linear search, the in linear search, the time complexity, the worst case is proportional to n, where n is the size of the array. In the binary search, what is the worst case? What is the worst case time complexity in binary search? So in binary search, you start with an array of size n, it becomes n by 2, and then it becomes n by 4. It keeps on going until it becomes, let's say, it becomes too small, like let's say 1. So that is approximately, so let's say n by 2 power k, if it is equal to 1, then this implies k is equal to log into the base 2. Yeah, you can think of time complexity as the number of operations. In this particular case, number of comparisons we can think of. So in the case of binary search, we will be able to do this whole search operation in log n to the base 2 comparisons. So like for example, if n is equal to 2 power 20, which is a huge number, in the case of linear search, you require 2 power 20 comparisons, but whereas in the case of binary search, you only require 20 comparisons. Do you see how there is a huge difference between this and this? But is there any catch in the binary search approach? Is there any catch? Yeah. So the catch in the binary search approach is we have to do sorted. The list should be sorted. So the catch here, the catch is array has to be sorted. So now, so the selection sort algorithm that you have seen, it kind of takes n square time algorithm, but there are algorithms to sort a list of n numbers using n log n. So the true cost of binary search is the time taken to sort, that is n log n. So there are algorithms to sort, and then log n to the base 2. That is the actual search. So does it make sense to use binary search? The time complexity of the algorithm, don't worry about it. So it takes n log n comparisons to make an array into sorted array. So there are algorithms. The selection sort requires n square time. It is not efficient, but there are other algorithms where you can do this in n log n time. Don't worry about it, guys. Just take this for my word, okay? So selection sort is not n log n. But there are algorithms like merge sort, quick sort, where the time complexity is n log n comparisons. But don't worry about it. But let's say sorting takes n log n time plus log n time for the search. So do you want to take this approach or this approach? Do you want to take the linear search approach or the binary search approach? Which one you would prefer? Binary, yeah? Binary search plus sort. Huh? Yeah, so Balaram has a nice answer. If you have to search only once, then linear search is better. But if you are doing search multiple times, then maybe it is better to sort and then do the search. Let's say if you are doing k searches, okay, the next challenge problem for you is this. Challenge problem is for what values of k is binary search better than linear search? What is k? K is the number of search operations that we are doing. Do you understand the challenge problem, guys? Are you with me on the challenge problem? If you take linear search, you don't need to sort the array or anything. You just go ahead and search. But if you take the binary search approach, you have to sort the array and do the search. If you are doing k searches, then no, then this is the time complexity of the you if you take the binary search approach. My question for you is under what values of for what values of k for what values of k does the binary search approach better than the linear search approach? Are you all with me on this question? This is the challenge problem. And I would like one of you to explain the answer to this challenge problem in the next class. Okay? All good? You're all with me in today's lecture? You just take log into the base to take some log. Okay? So you take for the first one, you take log 2. It's okay. Base has 2, no problem. You take the log as base 2. It's all right. Don't worry about it. Okay? If you want to use 2, you can use 2. It may not be 2, but it's okay. You can just assume it is 2. Okay, I think I would like to conclude today's lecture here. I think we looked at some excellent ideas in today's lecture, and I'm very happy to see your codes and very well written codes. And KUR. So K is greater than n log n divided by n minus log n. Okay, good, good. So I want others also to work out. It's a nice problem. Very nice problem. Okay, thanks KUR and thanks everyone. Wish you a very happy new year. And yeah, so keep up the energy. We will solve nice problems. I think, do we meet before January 1st? Yes, right? We'll meet on Thursday. Thursday is not January 1st, no? Okay, okay. Then I will hold my wish you happy new year. And so we will. You have to, by the end of uh, uh, you will have lab session this week, and the goal for this week is to solve problems from arrays chapter. But if you are lagging a bit behind in the arrays chapter, it is okay. We will give a little bit more time, but attempt to solve the problems from the arrays chapter this week. We will have a lab session. No problem. Don't worry about checking, guys. You solving the problems is important, na? Why do you care about evaluation? Kindly upload the lecture today itself. Okay. Don't worry about arrays is chapter 8. Yeah. Okay then. Yeah. You should. Oh, okay, okay. That is true. Yeah. I will. You will get access to OJ in the next couple of days. There's a bit of delay from my part. You'll get it by. What did we left 2D? We will revisit 2D array in the next class, but not much is there to the 2D array apart from this. But yes, we will revisit the 2D array thing in the next class on the Thursday class. But it's not much is there. So we looked at how to read two matrices, a 2D matrix, how to. There's only one technical question that is there that we kind of got an answer already in the class, but it's okay. Okay, have a great day, and I'll catch up with you on Thursday. Two problems for you to work. Binary search number 1. Number 2 is, what is number 2? Number 2 is, the challenge problem that for what values of k, this binary search is better than the linear search. These are the two things. Okay. Bye.